The map you grew up with is wrong. For decades, everyone knew where tornado country was. Kansas, Oklahoma, Texas, the flat open plains where the storms are so predictable. They named the place Tornado Alley. You learned it in school. You saw it on the news. But the storms didn't read that map. Right now, something is shifting. Tornadoes are hitting places that never used to see them. Families are losing everything in states where nobody had a storm shelter. Scientists are watching 70 years of data and asking the same question. Where is Tornado Alley now? We're going to chase that answer. We'll see why a tornado forms at all, and why the conditions for one have started sliding east. We'll go inside the deadliest outbreak in modern memory. We'll meet the people living in its path who have no basement, no shelter, and less than 13 minutes of warning. And we'll find out what happens when a storm moves into territory that was never supposed to be dangerous. Picture a Sunday afternoon in May. Church is out. Families are eating lunch. A high school graduation is filling an auditorium in Joplin, Missouri. Outside, the sky's doing something wrong. A greenish light is spreading across the horizon. The clouds are rotating. And then, at 5:34 in the afternoon, a supercell thunderstorm drops a funnel toward the ground, and the ground reaches back. Within 10 minutes, what started as a funnel cloud has become a monster a mile wide, carrying winds above 200 miles per hour. That is faster than any car on any highway, faster than most small planes, fast enough to strip the bark clean off a tree. The tornado moves through the heart of Joplin for 38 minutes. When it lifts, 158 people are dead. More than 7,000 homes are gone. The hospital is shredded. The costliest single tornado in American history has just happened in a city of 50,000 people, in a state that sits right on the edge of the zone everyone thought they knew. Joplin is not in the middle of Tornado Alley. It sits on the eastern edge of it, in Missouri, close to the line where the familiar danger zone was supposed to end, and yet the storm that hit it was the deadliest in recorded history. Scientists paid close attention. Something about where these storms were hitting had started to change. The word that researchers use is shift. Tornadoes are still tearing through Kansas and Oklahoma, but the numbers in those states have been falling. Meanwhile, the numbers in Missouri, Tennessee, Mississippi, Alabama, and Arkansas have been climbing. The bullseye on the map is moving, slowly, steadily, and for reasons that have to do with drought, warming water, and a jet stream that does not behave the way it used to. To understand how that shift works, you first have to understand the machine that makes a tornado possible in the first place. A tornado does not just appear. It is built, piece by piece, by the atmosphere following rules that have held since long before anyone put a name on a place called Tornado Alley. The machine is enormous. It starts hundreds of miles away, and what it builds, when everything lines up just right, is the most violent wind on Earth. The Joplin storm was one example, but the machine that made it has been running for millions of years, and it is running right now over a part of the country that is only beginning to understand what that means. Two Air Force officers in the early 1950s coined the phrase. Major Ernest Forbush and Captain Robert Miller were studying severe weather patterns over Texas and Oklahoma. They were already famous in weather circles for issuing the first modern tornado warning 4 years earlier, after a tornado roared across Tinker Air Force Base and flipped aircraft on the tarmac. When they mapped out where violent storms clustered most, they called the region Tornado Alley. The name spread. It stuck. And for the next 70 years, most Americans treated it like a permanent fact of geography, as fixed as the Rocky Mountains or the Mississippi River. The core of the original alley runs north and south through the Great Plains. Northern Texas, Oklahoma, Kansas, Nebraska. Flatland in every direction. No mountains to block the wind. No coastline to break the flow of air. That terrain is the first ingredient. The Great Plains sit in the perfect position to let two very different air masses crash into each other without anything in the way. The second ingredient is the Gulf of Mexico. Warm, wet air rises off that water and flows north, pushing deep into the middle of the country every spring. That air is heavy with moisture, the kind that feeds thunderstorms. It flows low across the land, hugging the surface. The third ingredient comes from the opposite direction. Cold, dry air slides down from Canada and off the Rocky Mountains, moving fast and flowing high. When that cold air runs over the warm, wet air below it, the warm air has nowhere to go but up. It rockets upward with enormous force. The rising column begins to spin because the winds at different heights are blowing at different speeds and in different directions. A rotating tower of air is born. Weather scientists call that tower a supercell. Picture a thunderstorm the size of a city, but organised, structured, rotating. Not a random cluster of clouds, but a single machine with a spinning engine inside it. A supercell can live for hours, travelling across the landscape, gathering strength. Most supercells produce large hail, severe winds and flooding. About 1 in 5 produces something else entirely. The spinning column tightens. The way a figure skater pulls her arms in to spin faster, the column of rotating air narrows and accelerates. The funnel descends. When it touches the ground, it is a tornado. The original tornado alley was the best address in the world for all 3 ingredients to arrive together. Warm Gulf air, cold mountain air, flat land, jet stream overhead. For decades, the storms followed the address. Then the address started to change, and a meteorologist sitting in an office in Illinois noticed something in the data that no one had expected. Victor Gensini had spent years chasing storms across the Great Plains. He was the kind of scientist who did not just study weather from behind a desk. He drove into it. He stood in fields watching the sky rotate. He understood what a supercell looked like from 100 yards away. And when he came back to his research and started plotting decades of tornado data onto maps, he saw something that stopped him. The dots were moving. The concentration of tornadoes, the dense cluster of activity that defined the original alley, was shifting east. States like Illinois, Indiana, Tennessee, Mississippi and Alabama were seeing more. States like Texas, Oklahoma and Kansas were seeing less. The pattern in the data was subtle but real. He published his findings in 2018, and the response was immediate. 500 media requests arrived overnight. Meteorologists, emergency managers, and government officials all wanted to know the same thing. Was the danger zone actually moving? Gensini had been careful in his language. He could show the trend clearly. The data was solid. He could say that tornado frequency was rising in the Midwest and Southeast and falling in parts of the southern Great Plains. What he could not say with certainty was exactly why. The answer he suspected involved several forces working together, and untangling them would take years of additional research. Other scientists came after him with their own studies. A team published a major paper in 2022 showing that large tornado outbreaks had shifted their centre of gravity toward the southeast over the previous 30 years. Another study, published in 2024 in a top atmospheric science journal, examined 70 years of data and confirmed the trend by multiple measures. The number of tornadoes in the eastern United States had gone up 12%. The number in the western part of the country had dropped 25%. The shift was real. The debate was no longer about whether it was happening. The debate had moved to something harder and more urgent. When scientists looked at where the new tornado hot zones were landing, they found something that made the trend far more serious than a simple change in geography. The storms were moving toward people who had never been told they needed to prepare for this. People without storm shelters, people in homes that a tornado could tear apart in seconds, people sleeping when the sirens went off. And that was before scientists started asking the next question, the one about what was actually pushing the storms east in the first place. The clue sat in the soil of Arizona. For more than 20 years, the American Southwest has been locked in a drought so deep and so long that scientists call it a mega-drought. Rivers that ran for centuries have shrunk to trickles. Reservoirs have dropped to record lows. The land has dried out so completely that the air above it has changed. Dry air is heavier and more stable than moist air. When you pile up enough dry air over a large region, it creates a dome of high pressure that sits over the western United States like a lid on a pot. That lid pushes weather systems around it. Storms that once tracked north through Texas and Oklahoma now have to go somewhere else, and the path of least resistance points east. The moisture they need to grow, the warm wet air from the Gulf, is still there, still flowing north, but now it meets the cold air further east than it used to. A meteorologist named Paul Pastelok described it simply. "The southern Great Plains are drying up," he said, "and when the moisture dries up in one place, the storms go looking for it somewhere else. the Gulf of Mexico is making that search easier. Water temperatures in the Gulf have risen on average by 1 to 2 degrees Fahrenheit over recent decades. That sounds small. But warmer water puts more moisture into the air above it, and more moisture means more fuel for thunderstorms. The warm, wet plume flowing north from the Gulf is now richer and more intense than it was 50 years ago. It pushes deeper into the Midwest and Southeast. The collision between that moist southern air and the cold northern air happens further east than it did when the original alley got its name. There is a third driver. The jet stream, the river of fast-moving air high in the atmosphere that steers storms across the continent, has been dipping further south into the Mississippi Delta region. Scientists connect this southward dip partly to the same drought conditions that are drying out the southwest. When the jet stream dips south, it carries the wind shear that rotating storms need right into the heart of what meteorologists now call Dixie Alley. All three forces are pushing in the same direction. The drought evicts storms from the plains, the warming Gulf feeds them once they arrive in the east. The jet stream gives them the spin they need to become dangerous. A system that once had a single address now has a new one, and the people living at that new address are about to find out something the residents of Kansas have known for 100 years. The name Dixie Alley is not new. A meteorologist named Alan Pearson coined it in 1971 to describe the region of the Deep South, where tornadoes had always been more common than most people realized. Mississippi, Alabama, Louisiana, Tennessee, parts of Georgia, Kentucky, and Arkansas. This zone had its own tornado problem long before any shift in the data. The shift has simply made a serious problem into a critical one. Storms in Dixie Alley behave differently from storms in the classic alley to the west. The difference is not in the wind speed or the size of the funnel. An EF4 tornado in Alabama carries the same destruction as an EF4 tornado in Kansas. The difference is in everything around the storm. In Kansas, when a supercell drops a funnel, you can see it from miles away. The land is flat, the fields stretch to the horizon, and the sky gives you a clear view of the rotating wall cloud descending. A farmer standing in a field has time to watch the storm, understand it, and make a decision. Visibility is a form of warning. In Mississippi, the trees close in. Dense stands of pine and hardwood line the roads and cluster around homes. The rolling terrain blocks sight lines. By the time a family hears that familiar sound, often described as a freight train bearing down, the tornado is already close. Heavy rain frequently wraps around the funnel, making it invisible even when it's near. You cannot see it coming. You only hear it, and then it is there. The season in Dixie Alley runs longer and stranger than in the classic alley. The Great Plains see their peak in May and June. Dixie Alley peaks twice, once in the late winter and spring, February through April. Then again in November and December, a second surge driven by fast-moving jet stream winds that make these storms move faster across the ground. A faster storm means less time for any given point on its path to be in the warning zone. Reaction time shrinks. Tornadoes in the region also hit at night far more often than storms in the plains. Scientists have found that about 60% of tornadoes in the southeast strike after dark. In the plains, that number is closer to 40%. A person asleep in a mobile home in rural Alabama struck by a tornado at 2 a.m. faces a set of dangers that a person in an Oklahoma farmhouse with a basement on a sunny May afternoon simply does not. The combination of those factors, the trees, the terrain, the timing, the season, the speed of the storms, adds up to a region that was already dangerous even before the data started showing more storms moving in. The next piece of the picture is why those storms, when they hit here, kill people at a rate that far exceeds what you would expect. In 1953, a tornado killed 116 people in Flint, Michigan. That record stood for 58 years until Joplin broke it. The reason records like these get broken in the east and the south, and not in the heart of the original alley, comes down to a single fact that barely anyone outside of meteorology talks about: mobile homes. Across the Deep South and the Midwest, a large share of the population lives in manufactured housing. These are homes built in factories and placed on land without full foundations. They are lighter than site-built homes, less anchored to the ground, and structurally unable to resist the lateral force of a strong wind. A well-built house rated to hurricane winds can sometimes survive an EF2 tornado. A mobile home in the same storm has almost no chance. The numbers are stark. Mobile homes make up somewhere between 8 and 12% of the housing stock across Dixie Alley. But they account for more than half of all tornado deaths that happen inside homes. A person sheltering in a mobile home when a strong tornado strikes is at 15 to 20 times greater risk of dying than a person in a conventional home. That gap exists partly because mobile homes lack basements, and a basement is the single most effective form of tornado shelter available. In Kansas and Oklahoma, storm cellars and underground shelters are woven into the culture. Families dig them, maintain them, use them. The architectural tradition of tornado preparedness runs deep. In the southeast, that tradition is absent. Most homes in Alabama or Mississippi sit on slab foundations or crawl spaces, partly because of the high water table that makes underground construction difficult and expensive. A family in those states seeking shelter has to find a small interior room on the lowest floor, away from windows, and hope the structure holds. That hope often fails, and when a tornado strikes at midnight, when the family is asleep, when the warning arrives on a phone somewhere in another room, the 13 minutes of average lead time that the weather service provides can shrink to nothing before anyone has moved. The vulnerability is concentrated in specific communities, rural areas where poverty limits housing options, small towns where mobile home parks cluster along the edges, places where the idea of a tornado was always something that happened to other people, in other states, on the other side of the country. The shift in the storm track is bringing the worst of the threat right into those communities, and the next question the scientists started asking is whether the storms themselves are also changing in ways that make them harder to predict. The number had been holding steady for decades. Roughly 1,000 tornadoes a year touch down across the United States. That number has barely moved. Scientists watching it expected that if the climate was changing the tornado picture, the count would climb. It did not. What changed instead was something stranger and more unsettling: the days. Back in the early 1970s, tornadoes spread themselves out. A typical year might see 150 days where at least one tornado touched down somewhere in the country. Quiet stretches here, active days there, the risk distributed across the calendar. A person in a tornado-prone area had many separate chances to get lucky, and many separate chances to be unlucky. But the threat was spread thin. Then the pattern began to change. Scientists started tracking a split. The number of days with tornadoes began falling. By recent decades, the average had dropped from roughly 150 days to about 100. But the total number of tornadoes stayed the same. Do the math and the result is unsettling. Fewer days, same count. The storms were bunching together. The calendar was developing empty stretches followed by violent bursts. An outbreak that once might have produced 20 or 30 tornadoes on a big day was now producing 50, 60 or more. Research published in the journal Science found that the worst outbreaks had roughly doubled in size over 50 years. In 1965, the most extreme outbreak expected in any 5-year stretch would have produced around 40 tornadoes. By 2015, that same 5-year worst case was closer to 80. The tornadoes were the same storms, the supercells, the wind shear, the rotating columns of air. But they were arriving in waves. Long quiet spells where nothing happened, followed by days of coordinated terror where the storms lined up across multiple states and marched east together. Meteorologists started calling these events tornado outbreaks, and the definition of a bad one kept getting worse. For communities in the new tornado zone, this clustering creates a specific kind of danger. A region with no history of major tornado events and no culture of preparedness does not build up readiness between outbreaks. A town in Alabama or Tennessee that goes years without a serious storm loses its edge, if it ever had one, and then the outbreak arrives, and it arrives all at once, and the warning window is the same 13 minutes it always was. April of 2011 belongs in any serious account of the shifting storm. The whole month was violent. An outbreak on April 14th through 16th killed 40 people across the South. That event has since been called the Forgotten Outbreak because what came less than 2 weeks later made it disappear from memory entirely. On April 27th, the atmosphere over the Deep South turned into a tornado factory. Meteorologists at the National Severe Weather Center had been watching the setup for days. They rated it a high-risk day, their strongest category, and placed the center of that risk over northeast Mississippi, South Tennessee, and northern Alabama. They were right about where. they could not stop what came next. More than 300 tornadoes touched down that day across 15 states. 4 of them were the most powerful rating possible. Alabama bore the worst. In Tuscaloosa, an enormous multiple vortex tornado more than a mile wide tore an 80-mile path through the city and into Birmingham, killing 64 people and injuring 1,500 more. Debris from that tornado was spotted falling out of the sky over Birmingham more than 20 miles away. In all, Alabama lost more than 230 people that day. The outbreak as a whole killed over 300 across the southeast. The storm tracked through a densely populated university city live on television. Cameras captured it moving through neighborhoods in real time. The footage was devastating and clear. It was also proof of how different this terrain was from the open plains. The funnel was surrounded by trees and buildings right up until it was on top of people. There was no long, clear view, no time to watch it cross a field and make a decision. It was in the streets before anyone had processed it, Congress noticed. In the aftermath of the 2011 outbreak, legislators funded a new research program focused entirely on why the Southeast was losing so many people. Scientists who had spent careers chasing storms across Kansas and Oklahoma now pointed their instruments at Alabama, and what they found in those hills changed what everyone thought they knew about how tornadoes work in complex terrain. The research program was called the Verification of the Origins of Rotation in Tornadoes Experiment Southeast. Scientists from dozens of universities and government agencies drove into northern Alabama, set up mobile radars on ridgelines, and spent multiple spring seasons waiting for storms to develop over the Appalachian foothills. What they found surprised them. The terrain mattered in ways that had not been captured in any previous model. Hills, ridges, and valleys were interacting directly with rotating storms on a scale smaller than anyone had anticipated. A tornado crossing a ridge might intensify slightly due to the terrain forcing air upward at the base of the funnel. A valley might channel the wind in ways that change the storm's path by a mile or two. On the open plains, that kind of small shift was irrelevant. In a landscape of small towns and forest-lined roads, a 1-mile path change was the difference between hitting a neighborhood and missing it. One researcher described the challenge of chasing storms in this territory compared to the plains. On the plains, a supercell might move 20 to 30 miles per hour, giving a team time to position and reposition. In the southeast, storms moved faster, the hills blocked the view, and the rain wrapped around the funnel so completely that radar was often the only way to track it at all. The researchers were, as he put it, calibrated for the plains. The southeast was a different problem entirely. This terrain effect also made the standard forecasting tools less reliable. Radar systems scan the atmosphere in broad sweeps, and the gaps between sweeps can be several minutes wide. A tornado that forms and dissipates in 2 minutes may never appear clearly on any scan. In the southeast, where squall lines and fast-moving storm systems were common, this gap was a serious problem. Storms were spinning up and dying before the radar caught them. Warnings were arriving late, or not at all, and the communities in the path had no way of knowing that the system designed to protect them was struggling to keep up. The scientists brought their data back to the labs and started building better models. The work was not finished quickly. It may never be fully finished. The atmosphere over the southeast is more complex than anything the original tornado research programs were designed to handle, and in the meantime, the storms kept coming. The second kind of tornado hiding inside the new storm track is one that barely registers in most people's mental picture of what a twister looks like. It has no classic funnel descending from a dark green sky. It has no wall cloud. A storm chaser would have trouble spotting it even from close range. Researchers call it a squall line tornado, and it is the quiet threat inside the larger story of the shifting alley. Squall lines are long walls of thunderstorms that can stretch for hundreds of miles. When a cold front pushes rapidly through a region, it can organize a continuous line of storms that sweeps across multiple states in a single night. Squall lines produce plenty of hazardous weather on their own, damaging straight-line winds, large hail, flooding. But they can also spin up small tornadoes along their leading edge. These tornadoes are usually weaker than the monsters that drop from isolated supercells. An EF0 or EF1 squall line tornado might only be on the ground for a minute or two. 1 minute is enough. The problem with squall line tornadoes is detection. A rotating supercell thunderstorm announces itself on radar with a signature shape and a hook that forecasters can track for hours. A squall-line tornado can form and vanish in the minutes between two radar scans. The average warning lead time for a supercell tornado is about 13 minutes. The average for a squall-line tornado is closer to 2 minutes. From the moment the tornado warning reaches a phone, a family in a mobile home in rural Mississippi has roughly the length of a TV commercial to reach any kind of shelter. These storms are disproportionately common in the southeast and far more likely to occur at night. They arrive wrapped in rain, hidden from view, embedded in what looks from the outside like a regular line of thunderstorms moving through. A family hearing thunder in the night, checking the phone, seeing a tornado warning appear for the county, has no way to know whether the rotation is 2 miles away or 20. And in the dark, in the trees, there is no horizon to scan. Scientists launched a dedicated field campaign to study squall-line tornadoes more closely, beginning in 2022. Teams spread out across the southeast with specialized radar systems, chasing the same storms that had been killing people for years without being properly understood. The knowledge they were gathering would eventually improve warnings, but the communities in the path were living in the gap between what was known and what needed to be known. Every 1% rise in a county's poverty rate is linked to a 2% rise in tornado fatalities. That relationship was documented by researchers studying decade after decade of storm data. The math is cold, and the meaning behind it is colder. A tornado is a physical event. It does not choose who it hits, but who survives, who rebuilds, who gets enough warning to reach a safe place, who has a safe place to reach at all. Those outcomes are determined by money as much as by the weather. In the poorest counties of Mississippi and Alabama, the picture is layered. Families in mobile homes are the most exposed, but the surrounding conditions multiply that exposure. A car is the fastest route to a sturdy shelter, but in counties where poverty rates run well above the national average, car ownership is not guaranteed. A family without a car in a tornado warning, living in a mobile home with no community shelter nearby, is running out of options at exactly the moment they need them most. Community tornado shelters exist, but access is uneven. Federal programs have funded some shelter construction in tornado-prone areas, but the pace has been slow and the coverage incomplete. A study of mobile home parks across the southeast found that the travel time from those parks to the nearest shelter frequently exceeded the entire average warning window. The shelter was real, funded, built. It simply could not be reached in time. The burden falls hardest on communities that are also least equipped to recover once a storm passes. After a tornado destroys a mobile home, the path to rebuilding is steep. Insurance coverage is often minimal or absent. Federal disaster assistance requires documentation, appeals, and waiting periods. Families living paycheck to paycheck, already without savings, face a gap between the moment of loss and any meaningful help that can stretch for months. For some, the gap is permanent. They do not rebuild. They move in with family, relocate, or find another mobile home and start the cycle again. Researchers who study tornado vulnerability have started using the phrase compound risk to describe what is happening in these communities. The storm is one layer, the housing type is another, the poverty is a third, the lack of transportation is a fourth. Each layer multiplies the others. The compound risk of the southeast is unlike anything that existed in the original tornado alley, and it is getting worse as the storms themselves shift east into territory, where none of these layers were ever expected to meet. A tornado warning used to look like a box drawn around a county on a map. An entire county would receive the warning, from the farms on the edge to the downtown, regardless of where the tornado was actually headed. In a county covering hundreds of square miles, most of the people receiving that warning were not in danger, and because they received warnings for storms that missed them, over and over, the warnings stopped feeling urgent. After the Joplin disaster, investigators found that the majority of residents had heard the sirens and not moved to shelter. They were waiting for more information. They had heard sirens too many times before for storms that did not materialize nearby. The word that investigators used in their report was harrowing. The people were not foolish. They were doing what months of experience had trained them to do. The warning system had, without intending to, taught them to wait. The response from the Weather Service was a fundamental rethinking of how warnings were communicated. The old language was clinical. A new approach introduced what meteorologists called impact-based warnings. A warning for a potentially deadly tornado now included phrases like catastrophic damage expected. It stated directly that people should take cover immediately. The goal was to break through the numbness of repeated false alarms with language that was unmistakably specific about what was coming. The geographic targeting also improved. Polygon warnings replaced the county-wide boxes, drawing boundaries around the actual path of the storm. Cell phones began delivering those warnings directly to people inside the polygon, meaning only those actually in the path received the alert. That change reduced the false alarm experience for millions of people in surrounding areas. It did not fully solve the problem. Radar gaps still existed. Detection of squall-line tornadoes remained difficult. The 13-minute average lead time had improved over previous decades, but had not extended enough to change the equation for people living far from any shelter. The engineers and meteorologists working on this problem understood that a warning system is only as good as the actions it produces, and the actions were still too slow, in communities too unprepared, facing storms too fast, in the dark, in the trees. The warning system was getting better. The question was whether it could get better fast enough. The current radar system covering the United States has been watching storms since the late 1980s. The dishes are mechanical. They rotate. They scan the sky from bottom to top in a sweep that takes between 4 and 5 minutes. 4 minutes is long enough for a supercell to travel several miles. It is long enough for a squall-line tornado to appear, tear across a neighborhood, and vanish before the next scan completes. The system was a revolution when it was deployed. By the measure of what it needs to do today, it is beginning to show its age. Engineers at the National Severe Storms Laboratory have spent years developing a replacement. The new technology uses a flat panel covered in thousands of tiny individual antennas instead of a single spinning dish. Each antenna can be steered electronically, which means the radar can look in multiple directions almost at the same time. A full scan of the sky above a storm takes less than a minute. The same coverage that currently requires 4 to 5 minutes could be achieved 8 times over before the old system finishes its single pass. One meteorologist in the control room during a test described watching a tornado develop through the new system's faster refresh. The rotation was visible in the radar data before it reached the surface. The warning went out earlier. The lead time extended. Minutes that previously did not exist were suddenly available. The technology has been demonstrated successfully. In April of 2026, it was used in an operational setting for the first time, helping forecasters warn of a tornado in Oklahoma with unusual clarity and confidence. The forecaster who used it said the data felt like watching stop-motion film compared to a live feed. The old system was the stop-motion. What the new system offered was something closer to watching the storm breathe. Rolling out the new system nationally will take years and significant funding. The existing network of nearly 160 radar stations would need to be replaced or supplemented. Budget pressures have complicated the timeline, but the engineers working on the problem believe that faster radar alone could add several minutes to the average tornado warning window across the country. For a family in rural Mississippi with nowhere underground to shelter, several minutes is the difference between reaching an interior hallway and standing in an open room when the roof comes off. In the spring of 2023, a tornado formed over the Mississippi Delta at night and spent more than an hour on the ground. It moved fast, faster than a storm of that type should have moved, covering nearly 60 miles before it lifted. The community of Rolling Fork, Mississippi, a small town of fewer than 2,000 people, sat directly in its path. The storm hit in the dark. Rolling Fork had no underground shelters. A large share of its homes were mobile and manufactured housing. The poverty rate in the surrounding county ran well above the national average, and a significant portion of residents had no car to drive to any shelter, had there been one nearby. The tornado tore through the center of town, flattening roughly 300 homes and businesses, killing 17 people inside the town alone. By the time the sun rose, the mayor of Rolling Fork was on camera telling reporters that his city was gone. He said it plainly, without drama. The buildings where people had lived were no longer there. The streets were buried under debris. The town that had existed the evening before did not exist in the same form any longer. Researchers studying the event noted how precisely it fit the risk profile that had been building in the data for years. Rural location, nighttime strike, high mobile home density, high poverty rate, limited shelter infrastructure, no deep-rooted tornado culture. every factor that made a storm deadlier in Dixie Alley than in the Great Plains was present in Rolling Fork. The storm did not find that combination by chance. It found it because the region where those conditions cluster most tightly is exactly where more storms have been going. 1 year later, the County Emergency Management Director attended a memorial service for the victims. While he was at the church, a new tornado touched down. The only home it damaged was his. The storms were still coming. Tornadoes have always been a problem of timing. The average warning lead time is 13 minutes. That number has improved substantially since the 1980s, when warnings often came with less than 5 minutes to spare. The improvement came through better radar, better computer models, and a growing understanding of the atmospheric signals that appear before rotation reaches the ground. But 13 minutes is an average built across every kind of warning event. The powerful supercell tracked for an hour, and the squall line twister that appears in a 2-minute radar gap. Those two events pull the average in opposite directions. For the deadliest category of storms, the ones that form in lines and travel at night in the southeast, 13 minutes is often an overestimate of what any real family actually receives. Scientists building the next generation of forecasting tools are attacking this problem from multiple angles. Machine learning systems trained on decades of radar data can now identify patterns in the atmosphere that human forecasters sometimes miss. They can flag subtle signatures in wind speed, temperature, and moisture that precede tornado formation by longer than any traditional method. Some of the early results suggested that these systems could extend effective warning times by up to half an hour compared to current methods. Half an hour is transformative. Half an hour is the difference between a family in a mobile home in Tennessee having time to drive to a community shelter, and that same family hearing the siren and having nowhere to go. The research is promising. The technology has not yet been deployed nationally. The gap between what scientists can demonstrate in a laboratory and what reaches a phone in a rural county remains significant. What is already in the field, already operational, is the change in warning language that came after Joplin. The words on a tornado warning now carry the weight of what scientists know about false alarm fatigue and the way people make decisions under threat. A warning today is more specific, more direct, more designed to produce the action that saves a life. The system has improved in every measurable way. The storms have not slowed down to match it. March of 2025 arrived in the southeast like a reminder that the calendar had changed. The traditional tornado season in the Great Plains peaks in May. March used to be a warm-up month, a time for scattered smaller storms, nothing that would make a record. 2025 broke that assumption completely. 2 massive outbreaks struck in the same month. The first, from the 14th to the 16th, sent storms across more than a dozen states from Arkansas all the way to Pennsylvania and produced 118 confirmed tornadoes. It became the largest outbreak ever recorded for the month of March. An EF4 tornado in Arkansas produced wind speeds of nearly 200 miles per hour. Long-track storms carved paths through Mississippi, Alabama, Missouri, Illinois, and Indiana. By the time that outbreak ended, 44 people were dead. 2 weeks later, a second outbreak added more than 100 tornadoes, this time focused in a corridor from Arkansas into Iowa and east. Mississippi, which averaged around 80 tornadoes in an entire year, had already logged 92 by the end of March alone. This single tornado from the first outbreak was ultimately surveyed as a continuous track stretching 117 miles across 2 states, one of the longest in recorded history. By early April, the country had seen nearly 500 tornadoes, almost double the historical average for that point in the year. Researchers who had spent decades documenting the gradual eastward shift of tornado activity had rarely seen the trend expressed so abruptly. March had never looked like this before. Climate scientists noted that the conditions that drive March tornado outbreaks, warm and early moisture from the Gulf meeting jet stream energy, further south than usual, were exactly the conditions that projections had been pointing toward for years. The calendar was changing, the season was starting earlier, and the storms were landing in the places where earlier chapters of this story have described the danger being greatest. Scientists trying to project what American tornado geography looks like by the end of this century face a problem that makes every other climate question harder. Tornadoes are too small. A tornado a mile wide occupies a speck on a global climate model. The computers that run those models divide the atmosphere into grid boxes dozens of miles across. A tornado fits inside a single grid point. Climate models cannot see them directly. Two researchers at Northern Illinois University spent 2 years running a different kind of model. They used regional simulations at much higher resolution, small enough to capture the conditions that make supercells form. Then they applied the projected changes in temperature, moisture, and wind patterns from larger climate models to their regional system and asked, what do supercell environments look like in a warmer world? The results were specific. A study published in 2023 projected a nationwide increase of nearly 7% in supercell frequency by the end of the century under moderate warming. But the national average masked enormous regional differences. In parts of the Deep South, the projected increase was far larger. Some specific locations in Mississippi and Alabama were projected to see roughly 1 additional supercell per year, above their current average by 2100. The season would start a month earlier. The greatest increases would come in February, March and April, exactly the months where the most recent outbreaks had already been breaking records. The study could not say directly that more supercells mean more tornadoes. The relationship between supercells and tornadoes is complicated enough that the question requires its own set of projections still under development. But supercells are the factories that produce the most violent tornadoes. A world with more supercells over the southeast starting earlier in the year is a world that has moved the most dangerous weather farther from the places equipped to handle it. May 16, 2025 was a Friday afternoon in St. Louis, Missouri. It was the middle of the workday. People were at offices and schools driving home. The city had not been struck by a significant tornado in living memory for most of its residents. St. Louis is a major American city, home to hundreds of thousands of people, and tornadoes were something that happened to smaller towns, to rural areas, to the kind of places that appeared in news coverage only when the damage was catastrophic. At 3:39 in the afternoon, a supercell dropped a funnel over Clayton, a suburb just west of the city. The tornado was 1.5 miles wide at its peak. It tracked nearly 12 miles through some of the most densely built neighborhoods in the region, cutting through Forest Park, crossing into North St. Louis, and continuing into Illinois before it lifted. 5 people died, 38 were injured. More than 5,000 buildings sustained damage, and the total cost reached $1.5 billion. The city's mayor stood before cameras that evening and said her city was grieving. The fire department had checked every building in the affected zone for survivors. The St. Louis tornado was not in Dixie Alley. Missouri sits at the northern edge of the shifting storm zone, one of the states where researchers had been documenting a steady increase in tornado frequency for years. St. Louis was exactly the kind of large, dense, unprepared city that scientists had been warning about, the kind where the combination of high population, older building stock, and limited tornado culture could turn even a mid-range storm into a mass casualty event. The storm that hit it was an EF3, powerful but far from the strongest tornadoes on record. The damage it produced was among the costliest the region had ever seen. The data behind the shift in tornado geography had been accumulating for years, confirmed by multiple studies, tracked by researchers, presented in scientific journals. May 16th was what that data looked like when it arrived in person. Cities have been growing outward for 70 years. Suburbs that did not exist in 1960 now hold hundreds of thousands of people. Shopping centres, office parks, and neighbourhoods of single-family homes stretch from old city centres across land that was open field a generation ago. Meteorologists have a name for what this means in tornado country. They call it the expanding bullseye. The logic is straightforward. A tornado path is fixed. It touches down somewhere, carves its width across the ground, and lifts. The damage it causes depends partly on what it hits. A tornado that crossed a cornfield in 1950 caused minimal harm. The same path through the same geography in 2025 might cross a shopping centre, a school, and 3 apartment complexes. The storm is identical. The world it travels through has changed completely. Researchers have found that the footprint of American development has grown by more than 600% in the past 80 years. The population has more than doubled. Every new subdivision built in the southeast Midwest, every sprawling development on the outskirts of a mid-sized city, adds a new set of targets to paths that tornadoes have been crossing for centuries. The storms do not aim at people, but more people keep moving into the paths. The expanding bullseye effect explains something that otherwise seems contradictory. Long-term normalized data, which adjusts tornado damage for how much wealthier and more populous the country has become, shows that overall tornado damage costs have actually declined since mid-century. Fewer of the strongest tornadoes are occurring today than in the 1970s. The warning system has improved enough to save thousands of lives that would have been lost under the older system. These are real and meaningful gains. And yet the raw damage numbers from individual outbreaks keep setting records. Every year seems to produce at least one multi-billion-dollar tornado event. The shift is not a contradiction. Fewer storms, better warnings, but more people in the path. The storm does not need to be stronger to cost more. It only needs to arrive where the houses are. Scientists studying the intersection of population growth, tornado geography, and the Eastward Shift project that tornado impacts could double again before the end of the century, even without any increase in storm intensity. The storms are moving toward the people are also moving toward the storms. 12 years passed between the last EF5 tornado in the United States and the next one. The EF5 rating sits at the top of the scale, reserved for storms whose winds exceed 200 miles per hour. Scientists joke that an EF5 tornado requires not just the right atmospheric conditions, but also the right target, something heavy enough to reveal what the wind is capable of. A tornado at that strength crossing an empty field leaves evidence that is hard to measure. A tornado at that strength crossing a farm leaves wreckage that tells the story. On the night of June 20th, 2025, a tornado dropped out of a severe storm system near the small town of Enderlin, North Dakota. It was after 11 at night. The tornado was a mile wide. It stayed on the ground for just under 20 minutes, killing 3 people and carving a 12-mile path through rural land. In the days after, surveyors rated it at EF3, a strong but not record-breaking storm. Then the engineers arrived. They looked at a derailed train. They found tanker cars thrown nearly 500 feet from the tracks. One grain hopper, loaded to full weight, had been flipped as if it weighed nothing. A farmstead had been swept clean from its foundation. The concrete slabs scoured bare. They applied forensic physics to the debris fields and sent the analysis to a review team. In October, the rating was upgraded to EF5, with estimated peak winds above 210 miles per hour. The 12-year gap between that storm and the previous EF5 had produced a question in the meteorological community. Were the strongest tornadoes becoming rarer? The evidence was not clear. Some researchers pointed out that the EF scale was applied more conservatively after it replaced the older rating system. Strong tornadoes might be receiving lower ratings than equivalent storms would have received decades earlier. Others noted that improved warning systems meant fewer buildings were fully occupied when the strongest storms hit, which reduced the damage markers that trigger the highest ratings. Enderlin answered the question with a single falling train car. The storms capable of that kind of violence are still forming. The 12-year gap was not a sign that the most dangerous tornadoes were disappearing. It was a sign that most of the paths they cross do not yet hold anything heavy enough to prove how strong they are. The person who taught most Americans what a tornado warning should sound like was a television meteorologist in Huntsville, Alabama, named James Spann. He had been on the air during storms for decades when the 2011 outbreak arrived. For hours on April 27th of that year, he stood in front of his maps and talked his audience through what was happening to their state. He named neighborhoods. He described what a rotating wall cloud meant. He told people where the tornado was, where it was headed, and what they needed to do in the next 3 minutes. His broadcast became a model for how local TV meteorologists could save lives during an active outbreak. The lesson was specific. People needed information that was local, immediate, and clear. A warning polygon on a phone was necessary but not sufficient. Knowing that a tornado was approaching a county was less useful than knowing it was approaching your street. The gap between a county-wide warning and street-level guidance has been one of the persistent challenges of tornado communication. Radar can see the rotation. It cannot tell you which side of the street the funnel will cross. The storm chaser on the ground can see the funnel, but communicating real-time chaser position to the public during an active outbreak requires coordination that was difficult in 2011 and has improved considerably since. Social media has changed this in complex ways. A chaser posting live video from a quarter-mile behind a tornado gives thousands of viewers a visceral real-time view of the storm. It also creates uncertainty. A viewer in the storm's path watching a live feed must make a simultaneous judgment about where the storm is relative to their own location. That translation from visual feed to personal action requires a clarity of mind that a late-night siren does not guarantee. Emergency managers studying the gap between warning receipt and protective action have identified something they call milling. People mill. They call a family member, they check a second weather source, they look out the window. The average time between receiving a tornado warning and taking shelter is longer than the warning window allows. Closing that gap means more than better radar. It means better human understanding of how people process fear on an ordinary Tuesday night. The culture of tornado preparedness in the Great Plains was built over a century of close calls, church halls used as shelters, farm families who knew to watch the southwest sky in May. It was built into the architecture, into the basement that sits under every farmhouse, into the school curricula, into the annual tornado drills that children in Oklahoma grow up treating as routine. That culture is not transferable by satellite. It does not come with the tornado when the tornado moves east. A family in rural Tennessee or coastal Alabama, living through their first experience with a real tornado warning, does not have the mental framework that a Kansas family inherits from childhood. The Kansas family knows the sound of the siren is not a drill. They know the interior hallway. They know to stay away from the windows, and they know this without having to think about it, because they have heard the same instructions every spring for as long as they can remember. The Tennessee family is hearing this for the first time with 13 minutes on the clock. Emergency managers in the Southeast have spent years trying to close this cultural gap. Public education campaigns have expanded. Tornado safety messaging now runs on social media and through school systems in states that historically never prioritized it. Weather apps have made the specific details of warning polygons accessible to anyone with a smartphone. In counties that have installed outdoor warning sirens, the coverage is improving, but culture moves slowly. Preparedness habits build over generations. The data on tornado fatalities in the Southeast consistently shows that communities with longer exposure to tornado risk, the parts of Mississippi and Alabama that have been in Dixie Alley for decades, have better baseline response behaviors than newer high-risk zones. The communities now entering the highest risk zone for the first time are starting from scratch. Some local governments have taken direct action. Community shelters have been funded in counties where mobile home density is highest. Schools in tornado-active states have been retrofitted with safe rooms that double as gymnasium space, making the shelter a daily presence in children's lives rather than an abstract emergency plan. In Moore, Oklahoma, the city became the first in the country to require new homes to be built to withstand winds of 135 miles per hour, nearly 50% stronger than the national baseline. The homes built under those codes survived the next outbreak significantly better than homes built under the old standard. June 17, 2026. A tornado drops over Effingham, Illinois, a mid-sized city in the center of a state that had not, until recently, been discussed as a tornado hotspot. The storm tears through downtown, collapses a building, and is gone in minutes. When meteorologists add it to the year's tally, Illinois is already well past its all-time annual record for tornadoes, with months left in the season. By midsummer of 2026, Illinois has confirmed more tornadoes in a single year than any state had ever recorded this early in a calendar year. Indiana has broken its own all-time record. Wisconsin, which averages 23 tornadoes in a full year, has already logged more than double that figure by the end of June. Missouri has surpassed its annual average for the fourth consecutive year. Victor Gensini, the researcher whose 2018 study first put numbers to the shift, is watching the season unfold from his office in Illinois. He is not surprised. He said publicly what the data had been showing for years. Tornadoes have been happening with less frequency in the Great Plains over the past 40 years, he said. They have been happening with greater frequency in Illinois, Indiana, Tennessee, and the Mid-South. If the past 8 years have shown anything, he added, it is that the trends are continuing. He also gave specific advice. Everyone in the Midwest, he said, should have a tornado safety plan. Every person, whether they believe they are in tornado country or not. The question to ask is simple. Where are you going to go if a warning is issued? Answering that question in advance, before the siren, before the 13-minute clock starts running, before the phone lights up, is the preparation that saves lives. The question is not whether a tornado will arrive. The question is whether anyone is ready when it does. The question of whether climate change is causing the tornado shift is the most carefully worded question in all of severe weather science. Scientists who have spent careers studying the data choose their words with unusual precision when they answer it. They do not say yes. They do not say no. They say something harder, consistent with. The patterns are consistent with what warming physics predicts. A warmer Gulf of Mexico produces more moisture. More moisture fuels stronger thunderstorms. A destabilized atmosphere in the eastern United States, where cold air from the north meets increasingly rich moisture from the Gulf further east than before, creates more days where the ingredients for a supercell come together. The jet stream behavior that has been pushing storm tracks east is consistent with observed changes in Arctic temperatures, which are warming faster than the global average, and which scientists connect to a weakening of the polar vortex, the cold air system that contains Arctic weather in the north. Every one of those connections has observational support. None of them is a proven chain of cause and effect. Tornadoes are too small and too brief for current global climate models to simulate directly. The most honest statement available from the science is that the shift in tornado geography is happening. The direction of the shift matches what physics would predict in a warmer world, and the warming is indisputably real. Victor Gensini put it plainly in media interviews over several years. Clearly there is a climate change signal, he said. The laws of physics that govern atmospheric motions are agnostic about county, state, and country. They do not care about the political borders on the map. They respond to temperature, moisture, and pressure. Those quantities are changing, the storms are responding. The scientific caution about attribution is not a sign of doubt about the shift itself. The shift is measured directly in the data. The caution is about precision. How much of the shift is driven by the mega drought in the southwest? How much by Gulf warming? How much by jet stream changes? And how much each of those factors is itself driven by human-caused warming? That accounting is still being done. The storms are not waiting for it. A helmet in a tornado is not a metaphor. Victor Gensini said it directly when asked about personal preparedness. Most tornado deaths and injuries come from flying debris, he said, and a bike helmet provides meaningful protection to the head during shelter. The image is strange enough to stick, a person crouching in an interior hallway wearing a bicycle helmet while the walls shake. But that is precisely the point. The things that keep people alive in a tornado are often not what they expect. The most effective shelter is underground. A basement or storm cellar puts the earth itself between a person and the force of the wind. An EF5 tornado can strip a house completely from its foundation and leave the basement occupants alive. The same storm kills everyone in a mobile home. Underground is the difference between a survivable event and a fatal one, and for the communities now sitting in the highest risk zone of the shifting alley, underground is often not available. The next best option is an interior room on the lowest floor, away from windows, with as many walls as possible between the person and the exterior. A bathroom works, a closet works, a hallway works. The goal is mass, the structural mass of walls and ceilings absorbing the force of debris before it reaches a human body. Getting low matters, getting away from glass matters, putting something over the head matters. Community shelters change the math for mobile home residents. A hardened shelter built to government specifications within reasonable distance of a mobile home park gives those residents a survivable option that their housing does not. The walk or drive to the shelter has to happen within the warning window, which is why the location of the shelter relative to the mobile home park matters as much as the shelter's construction. A shelter 3 miles from the park with a 13-minute window is less useful than it seems. A shelter 300 yards away changes the calculation entirely. The technology of shelter has improved. Prefabricated above-ground safe rooms, bolted to concrete foundations, built from steel plate to federal specifications, can be installed in a residential yard for a cost comparable to a used car. They are not comfortable, and they are not large. They are designed to do one thing: keep the people inside them alive when the house around them is being destroyed. In communities where the basement is impossible and the shelter is far away, a single-family safe room is the bridge between the old tornado culture of the plains and the new high-risk terrain of the east. The animals knew. Old accounts of tornado events from the era before radar are full of the same detail. The cattle moved toward the fence line, the horses turned, the dogs would not come inside. Scientists have studied this phenomenon seriously enough to confirm that at least some of it is real. Large animals may sense infrasound, the deep, low-frequency vibrations that severe storms produce well below the range of human hearing. The pressure drop that precedes a tornado's arrival can fall faster than the human ear registers as sound, but fast enough to affect an animal's inner ear. This matters for a practical reason. Modern meteorologists have access to tools the animals do not need. Doppler radar, phased array prototypes, numerical weather models that ingest data from satellites and weather balloons and surface sensors across the country, and produce probabilistic tornado outlooks days in advance. The gap between what those tools can theoretically achieve and what reaches the public in time to produce action is where most of the innovation is now focused. Machine learning systems are being trained on massive historical databases of radar images paired with storm outcomes. They are learning to recognize patterns that precede tornado formation in ways that human forecasters, scanning a single radar display in real time, might miss. The systems can simultaneously process dozens of atmospheric variables across thousands of grid points. Early evaluations suggest they can extend effective warning times, not just by adding minutes to the leading edge of the warning, but by reducing false alarms, which makes the warnings that do arrive carry more weight. Infrasound research is also active. Arrays of sensors placed around tornado-prone regions can detect the low-frequency signature of a rotating storm at distances beyond radar range. Some experimental systems have detected tornado-producing storms before rotation appeared on conventional radar. That kind of preemptive detection, measured in minutes of additional warning, is what researchers are racing to bring out of the laboratory and into the field. The gap between the laboratory and the field is familiar. It is the same gap that has existed throughout the history of tornado science. Every tool that now saves lives, the tornado watch, the polygon warning, the cell phone alert, the impact-based language, was once a promising research result waiting for funding, deployment, and public adoption. The next generation of tools is in that same waiting room right now. The history of tornado forecasting is a history of people who saw the problem before the rest of the world did and spent decades convincing others to listen. Ernest Forbush and Robert Miller saw, in 1948, that a tornado could be predicted, at least in broad terms, far enough in advance to issue a warning. They were right, and the first forecast they issued, prompted by a tornado that had already hit the base where they worked, saved lives. But it took years before tornado warnings became standard practice. In the 1990s, a network of Doppler radars transformed the picture. The rotating signature inside a supercell thunderstorm, the signature called the mesocyclone, became visible on radar screens. Forecasters could see a tornado factory spinning up and issue warnings with minutes to spare before the funnel reached the ground. Average lid times went from near zero to several minutes, then to more than a decade of improvement that pushed the average above 13 minutes for the strongest storms. Each advance came with the same pattern. A problem became visible, researchers developed a tool, the tool required funding and political will to deploy, and then the tool saved lives in ways that were measurable, but never made the evening news because the stories that get told are the deaths that happened, not the deaths that were prevented. The next advance is in progress. Phased array radar, machine learning, infrasound detection, community shelter funding, impact-based warning language, and social science research on how people actually make decisions under threat are all being developed in parallel. The pieces exist. The urgency is clear to anyone who has been watching the data since 2018. Whether those pieces reach the communities that need them before the next major outbreak arrives is a question the science cannot answer. It belongs to the people who allocate resources and write building codes and fund the research that keeps the warning system one step ahead of the storms. There is a version of this story that ends with the warning system catching up. With better radar, faster alerts, community shelters within walking distance of every mobile home park, building codes that require new construction to withstand the winds that are coming, and a generation of children in Tennessee and Illinois who grow up knowing the same interior hallway drill that Kansas children learned before them, That version is possible. Every element of it exists somewhere, in some form, already working in some community. More, Oklahoma became the first city in the country to require new homes to be built to withstand higher wind loads, and the homes built under those codes survived the next outbreak significantly better. After the 2011 Alabama outbreak, Congress funded research specifically into the southeast tornado problem. After Joplin, the warning language changed. After every major event, some part of the system gets better. The version of this story that ends badly is also possible. Communities in the new high-risk zone continue to be hit by storms they were not prepared for. Mobile home parks remain the most dangerous addresses in tornado country without the shelter infrastructure to change that. The phased array radar network takes another decade to deploy due to budget constraints. The cultural shift in tornado preparedness in the Midwest and Southeast happens too slowly to match the speed of the atmospheric shift. Both versions are in motion right now. The storms are faster than the legislation. The data is ahead of the public awareness. The research that shows what is happening and what needs to be done has been published, peer-reviewed, confirmed by multiple independent teams, and discussed at every major meteorological conference for the past 8 years. What has not kept pace is the translation of that knowledge into the physical infrastructure, the shelters, the codes, the radar systems that would change what happens to real families on the worst nights. That gap is the central problem of the shifting alley. The science is not the bottleneck. The science is ready. The tornado that changed everything for the town of Joplin, Missouri, arrived with a warning. 24 minutes of lead time, double the national average, more than enough for anyone who heard the siren and understood it was serious to reach shelter. A significant share of the population did not move. They had heard sirens too many times for storms that missed them. The warning system worked. The communication failed. Every improvement in tornado warning technology runs into the same wall. The radar, the algorithm, the polygon, the phone alert can all function exactly as designed. A person has to receive the warning, understand it, believe it, and act on it in time. Each of those 4 steps is a place where the chain can break. Social scientists studying this chain have found that the most effective interventions are not technical. They are relational. A warning delivered through a trusted local voice, a meteorologist the community watches every night, a neighbour who's already moved to shelter and is calling to say they need to leave now. An emergency manager whose face appears on local television during the worst of it reaches people differently than an automated alert. Trust, built over years of accurate local communication, is the force that moves people when the clock starts. The lesson from Joplin, from the 2011 Alabama outbreak, from every major event where warnings existed but death still occurred, is that the warning system ends at the moment the alert is issued. What happens next depends on everything that came before the storm. The shelter that was or was not built, the culture that was or was not developed, the trust that was or was not earned, and the decision that was or was not made in the 13 minutes between the warning and the arrival of the wind. That is the full picture of what the shift in tornado geography means. New territory, new risk, new communities that have not yet built the culture and infrastructure that decades of experience created in the plains, and a window, measured in years and not decades, to close that gap before the storms close it for them. The map is being redrawn in real time. Illinois, a state whose name did not appear on any serious tornado risk document 50 years ago, now leads the nation in annual tornado counts year after year. Indiana has shattered its all-time record. Wisconsin is logging seasons that would have seemed impossible in any decade before this one. Missouri's state climatologist tracks the numbers with the same language that Oklahoma meteorologists once used. Persistent, accelerating, concerning. The data that Victor Gensini published in 2018 was called startling by many who read it. 8 years later, with each new season adding another line to the same graph, the word that researchers use more often is confirmation. The trend is not just continuing, it is expressing itself in real events, real communities, real losses, in ways that the data predicted and that the public is only beginning to feel. The old mental map of tornado country is one of the most stubborn things in American geography. It was built over generations, reinforced by every movie and news broadcast that showed funnel clouds over Kansas wheat fields, and it has the kind of staying power that only a deeply repeated image can achieve. The map says, danger lives over there. Over there is the plains. Over there is where you need a storm cellar and a weather radio and a habit of watching the southwest sky. Here, where we live, is safe. That map is costing lives. Every family in Tennessee or Illinois or Indiana who does not have a shelter plan because they do not believe they are in tornado country is operating on a geography that the storm stopped honouring before this decade began. The shift is not coming. It is here. It has been here. The records being set each year are not anomalies. They are the new shape of the risk. The scientists have done their part. They measured the shift, published the data, updated the models, confirmed the trend, and communicated the stakes. What the science cannot do is build the shelter, draft the building code, fund the radar upgrade, or sit with a family in a mobile home park in Alabama and help them understand that this spring, unlike the last several, is the spring they need to take the siren seriously every time it sounds. The stories that do not get told are the ones where the warning worked. A family in Mississippi who heard the alert at 11 at night, woke the children, drove 2 minutes to the community shelter, and waited in the dark while the tornado crossed the field behind their mobile home. They came out in the morning and the home was gone. They were alive. Those stories are the product of every improvement in the warning system since the first modern tornado forecast was issued in 1948. They are the product of the researchers who pushed for better radar, the emergency managers who pushed for community shelters, the meteorologists who pushed for impact-based warning language, and the social scientists who studied how people respond to fear. They are invisible in the way that prevented disasters are always invisible. The visible stories are the ones this script has told. Joplin, the 2011 outbreak, Rolling Fork, St. Louis. The families who did not make it to shelter, the communities that were not prepared, the warnings that went unheeded. Those stories are the measure of the gap that still exists between what the science knows and what the infrastructure delivers. Closing that gap is a solvable problem. The solutions are known. Underground shelters, reinforced safe rooms, stronger building codes, faster radar, machine learning systems trained on decades of storm data, community warning education programs, impact-based language designed to cut through false alarm fatigue. None of those solutions requires a scientific breakthrough. They require money and will, and the political decision that the communities now entering the highest risk zone deserve the same investment in preparedness that communities in the original Tornado Alley received over a century of accumulated close calls. The storms are already there. The question that remains is whether the preparation will arrive before the next outbreak does. Stand in an open field in Illinois on a May afternoon and watch the sky to the southwest. The clouds are building, the air is heavy. There is a greenish light at the edge of the horizon that experienced stormwatchers recognize immediately, and most people in this state still do not know to fear. 350 miles to the west, the air is drier. The storms that once formed over that ground now form here, over this field, over this state. The machine has moved. The geography of danger has shifted in a direction that the data measured and the storms confirmed, and the record books are now writing down every season. The scientist who first mapped the shift said the laws of physics are agnostic about county and state and country. They respond to conditions. The conditions have changed. The response is the weather. The weather does not care what the old map said. What gets to matter now is what happens next. The research that says the risk is here. The radar that is getting faster. The shelter that is or is not built. The culture that is or is not passed down to the next generation of children who grow up in states where no one thought to teach them what the southwest sky means in May. The tornado that forms over this field will not know it is crossing new territory. It will not know that the communities in its path are still learning the language of the siren. It will not slow down for the gap between what the science has established and what the infrastructure has delivered. It will travel at the speed the atmosphere allows, in the direction the wind dictates, and it will arrive with exactly 13 minutes of warning, or 8 or 2, depending on the kind of storm it is and the radar that happens to be watching. That is the full weight of what the shift means. A danger that lived in one place for a century has been learning a new address. The address is everywhere the data says it is. The data has been saying it for years. The map is wrong. The storms have already moved on.